Hi, this is Roger from Kanka Labs, and today it's about this sidereal clock. I will explain in a minute what it's about, and we will take a look inside and analyze the circuitry with a better view than the one you get now. And I borrowed this from the Public Astronomical Observatory in Aachen, my hometown. Just to check it and to adjust it, because the accuracy is of course dependent on how well the quartz crystal is set to its frequency. And so later we will adjust it, and I got out my venerable frequency counter from Electron magazine and just checked it with my rubidium frequency standard. So it's around 1 ppm out. That is sufficient for setting a clock, because we will also check the drift of the quartz with voltage and with temperature. As you can see there, this is not a quartz, well, if you can see it, this is not a, take out the clips here. The quartz is sitting here, and this is not an ovenized quartz or temperature controlled or somehow stabilized quartz. It's simply a simple quartz oscillator with a 4060 CMOS, and this drifts of course a lot with temperature and perhaps even with the supply voltage, with the mains voltage. We'll see how well the stabilizing of the DC supply voltage of the CMOS circuits is. And so that's why it's enough to have 7 digits, and the last one is 1 digit out after many years. I don't want to adjust this now, because the quartz here is in a self-built or home-built OCXO, oven-controlled crystal oscillator, and this is apparently drifted a bit over the last 10 years. And so first let's explain what a sidereal clock is for, and that this is not running with the same speed as a civil clock. So if we go to the Wikipedia entry about sidereal time, there's an explanation why a sidereal day and a solar day or civil day are not the same. The clocks for both are not running at the same speed. You might be a little bit surprised that the Earth does not rotate one full rotation in exactly 24 hours, but it does that in 11 hours, 56 minutes and 4 seconds. That is, if you look at this arrow here pointing to a distant star, you can see that from one day to the next, here we have the arrow in the same direction, and this takes, as I told you, 23 hours, 56 minutes and 4 seconds. But because the Earth has moved a little bit in its orbit, for looking again at the Sun, the Earth has to rotate a little bit further, and these are the missing 3 minutes and 56 seconds. This gives 12 hours for a civil day, but that is not one full rotation. It is one full rotation plus the time it needs to compensate for the movement in the orbit to view directly at the Sun. So that means that a sidereal clock is running faster than a civil clock, and the factor, we will need that later, is 1.0027379, and that is sufficient for us because we only need the first 6 places of the number. There's a very little variation with time because the Earth is a little bit slowing down, etc. But we need only this figure here, because our sidereal clock will have the 1 second input, not with 1 second as we would expect for a civil clock, but with 1.0027379 and so on hertz. So a little bit faster, 0.27379% faster than a civil clock. So, and you might wonder, well, What purpose does a sidereal clock have? Is this just a gimmick for astronomers so that they have their own time? No, there are or were really two things that you needed a sidereal clock in an observatory. Of course, in the old days, this was a mechanical clock, as you can see here, one from the Royal Observatory in Greenwich. The main two purposes are measuring one of the two coordinates of stars, planets, or other heavenly objects. So in the sky, we have basically the same coordinate system as on the Earth. On the Earth, everybody knows geographic latitude and longitude. We have nearly the same for objects in the sky, only there what we have on Earth as geographic latitude is called declination. That's one of the two coordinates. And what on the Earth is geographic longitude, that is called right ascension in astronomy. And both coordinate systems have the same axis. They are basically overlying, or you could imagine the celestial coordinates as a projection of the Earth coordinates. But there's one difference which you can see here in the animation. The geographic coordinates on the Earth are of course fixed to the Earth, while the celestial coordinates of a celestial object are fixed to the imaginary celestial sphere. And because the celestial sphere seems to rotate with respect to a fixed observer on the Earth, you have, of course, moving coordinates when you're standing on the Earth, or your telescope on its mount is standing fixed on the Earth. Then one of the coordinates, that is the declination, you don't have to care about it because that does not move, but the other one, the right ascension, is moving with respect to your fixed telescope mount. And therefore, that's the second and still modern purpose of using sidereal time. That is just using your setting circles to find objects in the sky. There you have your coordinates which you look up from a table. Let's say you want to see Pluto in your telescope. You look up the declination and right ascension of Pluto at that day that you are observing or want to observe it. And now you go with your declination to the setting circle of your telescope mount and set the telescope to declination so and so. But the right ascension you cannot set directly because of the moving celestial sphere. You have to make a subtraction and to get what is called the hour angle. And this subtraction is simply the sidereal time minus the right ascension. I will show you an example in a second, because I have another sidereal clock which does this complicated subtraction. Complicated because you have to subtract hours, minutes and seconds from each other, which does that automatically. But nevertheless, you finally get from that subtraction your hour angle, and that is the second coordinate you are setting your telescope setting circle just to find your object. And that's why you need the sidereal time to use that hour angle setting circle to find your objects without eternally searching for them in the finder scope. Okay, here you can see the principle how this works with getting your hour angle out of the sidereal time and the right ascension coordinate. Here we have the running sidereal time. This is also for the public observatory in Aachen. And now with these thumb switches, you set the right ascension coordinate of your object that you want to observe. So if you subtract 10 hours, 52 minutes and 30 seconds from the running sidereal time, you get this as the result. So that makes, especially in the night when you're tired and just for not making any errors in this subtraction, and the value here, which is designated here as h.a dot, which is simply the abbreviation for hour angle, You read the hour angle, go to your telescope, go to the setting circle with the hour angle, set it to 7 hours, 45 minutes and so seconds. Usually they are divided only with whole minutes and not seconds. And then the object that you want to observe is centered in your eyepiece. That's just the second very important purpose for having the local sidereal time at least exact to, let's say, half a minute. And the usual quartz with, let's say, 20 ppm accuracy and a large temperature coefficient will gain or lose these 30 seconds in a matter of days. So to have your sidereal clock running exactly for at least a few months and not having to reset it constantly every night, it should have an accuracy of a few ppm constant with temperature, because you can imagine that the temperature in an observatory can be during the day as high as 30 degrees Celsius and in the night as low as -20 here in Germany. Or let's say -10 because of the climate change, or 0 degrees Celsius as a minimum due to climate change. So that was it for a short explanation what sidereal time, hour angle and the right ascension coordinate is used for. And now we'll take a look at the circuitry and how this sidereal clock is really working. So that's what it looks inside. Let's take a short overview. We have our 220 or now 230 volts mains cable coming, a little transformer. Here is the power supply with the 4 rectifier diodes, a big electrolytic, and this is a 7812 12 volt regulator. So then here we can see the oscillator part with a little capacitance trimmer to trim the standard quartz to its frequency. We can read 3.579545 megahertz. I'll note that down because we later have to calculate by the different divider ratios what will come out of that. And the oscillator is simply the standard oscillator with the 4060 CMOS oscillator and divider. So the first divider stages are also used here. The oscillator frequency can be checked here, but this is the direct oscillator pin. And of course by stray capacitance, if you connect a probe to this pin, of course the oscillator frequency will change. So this is not a good idea to trim the frequency directly at the output of the oscillator itself. So we will later check simply the 1 Hertz or 1.0027379 Hertz at the Hertz input. We have a few divider stages realized with 4040 binary ripple counters, and we will probe just in a minute the divided frequencies. And the rest are some standard logic gates, for example also for the PWM modulation of the brightness. The brightness can be turned down nearly to 0 because in an astronomical observatory at night you of course don't want any too bright LEDs, and this is simply realized with PWM control. And here you can see the little transistor which works as the kind of current switcher for the LED display. And the rest is quite simple. We have 6 CMOS 4029 synchronous up or down counters, which can be used as binary or decade counter. And with these, as you will know, the first one resets every 10 seconds, then gives a pulse to the 10th seconds, and they only go up to 6, so they will reset and give a pulse to the minute when they reach 6. So therefore you can see there are a lot of diodes, and with these diodes the different maximum count values or the divider ratios are realized. For example, the second counter only counts to 6, as well as the fourth counter, because seconds and minutes are realized, of course, the same way. And a little bit more complicated are, of course, the hours. Usually the ones of hours give a pulse to the tens of hours every 10 hours. But when all in all 24 is reached, then there is a reset for both of the counters. But that is standard diode controlled divider setting with these counters. And then, of course, for every digit, for every 7-segment display, we have a BCD to 7-segment latch decoder and driver and the current limiting resistors. So all in all, standard CMOS digital logic, which could have been realized from the mid-19 or even early 1970s. But I'm quite sure that this sidereal clock was built in the 1980s, perhaps even in the 1990s. What is not so good is here this simple piece of loose aluminium as a heatsink that can wiggle if you would have a lot of vibration here, that by wiggling could break one of the pins of the voltage regulator. But nevertheless, this clock is standing still without any vibration. Do we have anything else? If you look at the front, we of course can set the time. So they made this setting the clock in a very special way. If we put the switch to the set position, then if we press the hour set, it is just only the minutes and the hours are running fast. And with the minutes setting, it is incrementing about 1 minute per second, but the seconds remain always at 0, so you have to set the switch back to run again when exactly the next minute is reached. So when you pre-calculate the momentary sidereal time for your geographic longitude, you need the next minute, and then when this minute is reached, you set it back to run, and then it starts with 0 seconds. So that is all there is inside, and let's do some probing. The first thing I'm interested in is how clean is the DC voltage and what DC voltage are they using, because we have an additional Zener diode as it looks here and a 5th power diode. So let's see. I have to do this in a way that you still can see the display of the multimeter. So the input voltage of the voltage regulator is a little bit higher than 14 volts. And the output is 11.8, so that's just at the border of the specifications, because you usually, as far as I remember, with the 78XX regulators, you need at least 2.5 volts more. So this is just slightly above 14 volts. This is not as it should be. Perhaps if we turn down the brightness a bit when it consumes less, yeah, then it goes up to 18, but with full brightness we only have 13 point, just jumping around a bit, around 14 volts at the input. And let's see if the output also changes. 11.8, and at 0 brightness, yeah, okay, it remains just constant, so it's just within specs. But what, and we will check this, what happens if the mains voltage goes down to, let's say, 210 volts? We can measure what the mains voltage is at the moment. So 233, nominal we have 230 in Germany, but this could go down to 210 or even slightly below 210. So next is the digital logic running with 11.8 or less, and it runs with 11 volts. So apparently this diode is an additional protection diode or whatever its purpose is. So we have one diode drop from the output of the 12-volt regulator. And so the first thing I've made out is the main frequency is divided inside the 4060 CMOS oscillator divider by a factor of 16. And this gives at the output that goes to the next divider stage 223.7216 kilohertz from the main quartz frequency. And this we can probe here and we get 223.7196. So this is a little bit off, but we still don't know if this is really the desired frequency. We'll follow the signal further. And the next divider divides that frequency by a factor of 101. And that gives 2.215 kilohertz. And let's see where we can probe that frequency. This should be present at this pin. And we get 2.215045, so of course also a little bit out, but we have the right frequency. And this must further be divided down by a factor of 2209, and that gives then 1.0027456 hertz. So that's a little bit off. It should be 1.00273791 rounded. And let's see if we find this 1.0027456. And this is at the input of the first counter. And there we find 1.002736, but it should be rounded 38. So we have to tweak the capacitance trimmer a little bit just to get this to the desired frequency of 1.002737. So that was the wrong direction. Now we have the last digits are 25. Now we are at 38, 1.002738 hertz. So that is the at least exact to 1 ppm. That is the right frequency for a second frequency or seconds frequency for a sidereal clock. And now we will check if this value changes or how much it changes with temperature and with the mains voltage. Okay, now I've switched in as a power supply for the sidereal clock my steppable isolation transformer. At the moment it's at 230 volts and we have our 1.002739 seconds signal. And let's go down 10 volts to 219. And the frequency remains constant. That is good. Another 10 volts to 208. Still okay. Another 10 volts. Okay. So the oscillator is not sensitive to changes in the mains frequency. Let's go up again and to the maximum that is allowed here in Germany, which is 240. And also we're now at, I can only step the transformer in steps of around 10 volts. So we are at 245, which is over the tolerance in Germany. So changes in the mains frequency apparently don't affect the oscillator. But now let's probe what temperature does with this freeze spray directly onto the quartz. And we're more than 10 ppm upwards. Let's see how long this takes to go down again. So it doesn't completely return to the initial value of 1.002738 Hertz. And that's typical of quartzes if you put a shock on them, and that must not be only a mechanical shock, it could be also a temperature shock, because with these freeze sprays, that's really a shock for the quartz. It's slowly returning, but we can't expect any better than 10 ppm over the temperature range that is inside the observatory dome. And so it makes no sense to adjust the frequency to better than 1 ppm because this simple quartz without any temperature regulation or compensation, it never remains exactly enough at the frequency that you want it to set. And we could try as a last try if the frequency changes when we turn down the brightness, but that apparently has no effect. So we're nearly back at the last two digits should be 38. We're now still, or 39. We're 2 ppm out, so that's okay. So it does return after a few minutes to nearly to its last set value. But the problem with this thing is no temperature compensated quartz, no oven controlled quartz, and you can't expect over the temperature range that is present in an observatory dome more than 10 ppm. That gives around 9 seconds per day, or the 30 seconds tolerance is after a few days when the temperature is not constant. So perhaps a week the clock will keep the time up to 30 seconds precisely. So that was it for today with a clock that you usually don't have anything to do with, a sidereal clock. And thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.